So this video will be about how the rate constant depends on temperature. So all the other examples we've talked about so far, we've given you a rate constant. It's called a constant because it does not depend on the concentration. However, it does depend on temperature. And so any rate constant that you see reported to you should actually have a temperature with it. If you don't have a temperature in a problem on an exam, assume room temperature if you need to. Okay, so the person who came up with the equation we're going to use, his name was Arrhenius, and he was actually the first person to kind of quantitatively predict how much global warming you should expect from carbon dioxide as a greenhouse gas. But we're going to use his equation for how the rate constant depends on temperature. So one form of that is going to be that the rate constant is equal to a prefactor A, which contains the units, times an exponential minus the activation energy divided by gas law constant times the temperature. Okay, so the gas law constant in the units of joules, which is what our activation energy units should be in terms of, 8.314 joules per mole Kelvin. Okay, so that tells you the temperature should be in Kelvin when you use this equation. Now this is an exponential, and this is something that we can transform to a linear equation by taking the natural log. So let's go ahead and look at the logarithmic form of this. Okay, so the natural log of the left-hand side is just going to be a log of the rate constant. Log of A times plus the log of this exponential, well, the log of an exponential is just going to be the exponent. And we're going to write the EA over R separately from the 1 over temperature. Because what we're going to do is think about if we were to plot natural log of K, that would be our y-axis. This would be our y-intercept. The slope would be the negative of the activation energy divided by the gas law constant R. Make sure that if this is in joules, then this is in joules. Frequently you'll have to convert kilojoules to joules. Don't fall into that trap. And the R also includes Kelvin. If temperature is given in degrees C, you must first convert all temperatures to Kelvin. All right, so if you were to plot natural log of K versus 1 over temperature, so it's a little more complicated than the first order kinetics equation would be. Then the slope will be the activation energy divided by the gas law constant R. Okay, so, and of course the slope should be negative because activation energy by definition is a positive number. Okay, so just to recap the idea of activation energy. So if we have an energy as the reaction progresses, so we have some sort of reaction coordinate, maybe a bond being made or broken or angle twisting or whatever, and this will be the energy, then this difference here is the activation energy, okay? It's the amount of energy you have to put into the reactants to get them to the point energetically where the reaction will occur. Okay, so what you can see from Arrhenius equation is that this has an exponential and it's a negative exponential dependence. So the higher the barrier, the smaller K is going to be. The other thing you can see is that the higher the temperature, then K is going to be much larger. Okay, so chemical reactions go much faster at higher temperatures, and they go much faster with lower activation energies. And so we will see in a lecture about mechanism catalysts act by lowering the activation energy. Okay, so let's actually work out a problem. Now, the important thing about the Arrhenius equation is to realize it has nothing to do with the order of the chemical reaction. So this is true for all chemical reactions as far as you're concerned. So we're going to say, okay, let's say we have a chemical reaction and the rate constant at room temperature and I'll just abbreviate temperature by T, and that's 25 Celsius, is 1 times 10 to the minus 3 molar minus 1 minute minus 1. Okay, so this is a second order rate constant of some sort. Again, it doesn't matter what the order is, but it does affect the units in A. So if K is molar minus 1, minute minus 1, this has to be molar minus 1, minute minus 1 units for this prefactor. Okay, so and we're going to call this T1 and rate constant 1. Okay, and so what we're going to do is we're going to look at or consider a plot of natural log of K versus 1 over temperature. That will be 1 point, and there will be another point. Okay, so this will be log of K1 and T1, 1 over temperature 1, and then this will be natural log of K2 and 1 over temperature 2. Okay, so the thing we'll want to know is what is the rate constant for the second point if the temperature is equal to 50, sorry. Okay. So the question is, what is the rate constant if the temperature for the second point is 77 degrees C? All right, so first thing is, since it's a higher temperature, we expect a larger rate constant. So we expect a number larger than 1 times 10 to the minus 3. The other thing to realize is that the linear form, well, y equals mx plus b is one form of the line, but there's also another form of the line, and that's the two-point formula. So this equation would be given to you on an exam, or else you could just work with this formula. So the two-point formula is that the ratio of the natural log of K2 over natural log of K1. Remember that the quotient, oh boy. All right, here we go again. Don't. Okay. The two-point formula for this equation is the natural log of K2 over K1 equals E sub A over R times 1 over T1 minus 1 over T2. Oh, nope. Off the screen. Try it again. Okay. So the two-point formula is going to be log of K2 over K1 equals activation energy over R times 1 over T1 minus 1 over T2. Okay, so, and again, it's still getting over there. All right, let's try it one more time. Oh. All right, let's try it in a different color. All right. So the 2-point formula is going to be the log of the ratio of the rate constants. And that's going to be equal to the activation energy over the gas law constant times the reciprocal of the temperatures, 1 over T1 minus 1 over T2. Okay, so let's work with this 2-point formula here. Well, basically we have 1, 2, 3, 4, 5 variables, and so far we only have 3 of them. So there's one other piece of information we need to know in order to solve this problem, and that's the activation energy. All right, and so the activation energy is 30 kilojoules per mole. That's a decimal point. All right, so now we have the activation energy 1K and 2 temperatures. So now we have 4 quantities. We can solve this. Okay, so let's just list every variable, and then I'm going to allow you to get your calculator out. All right, so K2 over K1. All right, so it may not be useful to actually put in the numbers for K yet, because we have the right-hand side with all these numbers. Okay, so let's just leave the left-hand side alone, and activation energy is going to be 30,000 joules. All right, and the reason we need joules instead of kilojoules is because we have the joules for the gas law constant. Okay, now I don't have room on the screen here, but the temperature 1 is 25 C, which is 298 Kelvin. And T2 is 350 Kelvin. Okay, so what you will see is if you actually get the points mixed up, that is to say, it doesn't matter if this is 0.1 and that's 0.2, but it does matter if you put the temperature with 0.1 with 0.2 and vice versa. So if you do that, if somehow get 2 values switched, you'll get an activation, you'll get the rate constant will be actually smaller at higher temperatures, and that probably tells you just made a sign error. If you're solving for activation energy, you'll get a negative activation energy. It just tells you probably just made a sign error. First thing to do is check for sign errors. Okay, so when you do all this, the natural log of K2 over K1 equals, all right, well, I don't know that number. Let's find that number. Okay, so I would suggest getting this parenthesis quantity first. So 298 reciprocal minus 350 reciprocal. That's 5 times 10 to the minus 4 times 30,000. Okay, and that's about 15 divided by 8.314. And so 1.8. Okay, so if you have a log of something is equal to 1.8, then that something is equal to e to the 1.8 power. So let's do e to that power. All right. Let's do e to that power. And we get 6. Okay, so the final answer is that the rate constant at the higher temperature is going to be 6 times faster than the rate constant at the lower temperature. And so that means 6 times higher than this is 6 times 10 to the minus 3. Molar minus 1, minute minus 1. All right, well, that's it. So you should be able to work any variation in this problem. Again, the key points to watch for are make sure your temperatures are in Kelvin, make sure that if you have kilojoules, you convert to joules if you're going to use R in terms of joules. And that the rate constant at the higher temperature should be larger. All right, that's it.